Let's get started. So I want to spend today telling you a little bit about a couple other proofs of the faithfulness of the action of the Braid group on the homotopy category of modules over the zigzag algebra. So I'll get to those proofs in due time, but maybe the first 10 minutes I just want to start by making a few kind of general remarks about where this question of faithfulness comes from, and perhaps suggest its relation to analogous questions in closely related areas. So I'm doing this in part because Jake introduced the Hecke algebra, and I think that there's a kind of interesting philosophical question if you're interested in the Braid group, which is which questions in the Braid group can be studied via the Hecke algebra and which cannot. I think I'll try to make that a little more precise in a moment. But let's forget the Hecke algebra for a moment. Let's suppose that we're studying the symmetric group, Sn. And so let's say we want to study the symmetric group via matrices. In other words, we want to find a faithful representation of the symmetric group. Well, of course you can. This is a finite group, so you could take the regular representation and that will work perfectly well. But that's not the best you can do. I mean, the trivial representation won't work, the sign representation won't work, but the next smallest representation will work. So you could take V, say maybe inside Cn, you could just look at vectors whose sum is 0. This is a hyperplane inside C to the n, and of course the symmetric group acts naturally here, just permuting the factors. This is an irreducible representation of the symmetric group, and this is a faithful representation of the symmetric group. And the dimension of V is n minus 1. So this is a much smaller faithful matrix representation of the symmetric group than would you do if you use the regular representation. Moreover, if you replace the symmetric group by an infinite Coxeter group, say by the free group, then the regular representation wouldn't give you a finite dimensional representation, but this guy does generalize to a finite dimensional representation for arbitrary Coxeter groups. That's sometimes called the reflection representation, or the dual reflection one, and it's a theorem of Tietz that representation is always faithful. So, so this is an important representation in the theory of Coxeter groups. Okay, so you could look at this and you could say, well, suppose I'm not interested in the symmetric group, but rather I'm interested in the Braid group. I want to try to find a faithful representation of the Braid group. Well, of course, there's a homomorphism from the Braid group to the symmetric group, so the Braid group acts here, but that has no hope of being faithful just because this group homomorphism has a kernel. So you might try to correct that defect. So how might you try to correct that defect? Well, one way to do it, I mean, one way to see one kind of first observation about the kernel of this group homomorphism is that the generators sigma I and sigma I inverse both get mapped to the same thing. So one way to correct this defect might be to try to deform this piece of the story by pushing off the positive crossing and the negative crossing in different directions. And that's exactly what you do when you pass from the group algebra to the symmetric group to the Hecke algebra. By introducing this variable q and looking at the Braid group action to the Hecke algebra instead of the symmetric group, you fix this problem. Sigma I and sigma I inverse no longer go to the same thing. So if you want to be a little bit, at first maybe naive attempt to construct a faithful representation of the Braid group would be to replace the symmetric group by the Hecke algebra defined over there. And then the Hecke algebra acts well. Now I need to introduce my Q into the story. So this representation, by the way, of the Braid group that goes through the Hecke algebra and just deforms this reflection representation has a name. This is called the Burau representation, or the reduced Burau representation, which is also has some topological meaning, which maybe we'll see a bit later. But so the Braid group maps the Hecke algebra, and in particular, you get this action of the Braid group here, and it's not at all obvious whether or not it has any hope of being faithful at first glance. We certainly fixed the most obvious defect, but it's not clear. But let's put that down as a question for a moment. So is the we're talking about reduced reduced Burau representation of Bn faithful? I'll tell you the answer in a moment, although I suspect many of you already know it. Okay, so well, now it doesn't make sense to say that this map is surjective anymore. We just have a map. This is a group. This is an algebra. It's a vector space. But let's just put another question very closely related to this one, but logically distinct. We could forget about this representation, and we could just look at this map from the Braid group to the Hecke algebra. And we could ask, is this map injective? So maybe this is question 1. Question 2 is the map from the Braid group to the Hecke algebra injective? This is allowing us bigger but still finite dimensional linear algebra to try to understand this. And just to put another analogous question on the board, an analogous question to these, for reasons which I'll maybe explain a little bit, is does the Jones polynomial detect the unknot? So if I think V was Jake's notation for the Jones polynomial. So if V of a knot is, if the Jones polynomial of a knot K is equal to the Jones polynomial of the unknot, is K the unknot? So does the Jones polynomial detect the unknot? So okay, so what's the status? Well, okay, so I'll say something about these questions in a moment. All of these questions have categorification. So let's write down the categorification. So this is like Q1 up, although I'm writing it below, which is a little unfortunate. So is the categorified Burau representation faithful? The categorified Burau representation is what we're studying here when we study this action on the homotopy category modules over the zigzag algebra. So I'll explain that a bit more clearly, but is the categorified Burau rep of Bn faithful? So I mean, there are other kind of analogous questions with categorifications we could put here. I think it would be fun to kind of generate as big a list as possible. So what would question 2 be? So question 2 is the content, well, not the question, but what to put this way, that was the content of Jake's talk. So instead of looking at the map from the Braid group to the Hecke algebra, we look at its categorification, which is the map from, so is the map from the Braid group to the homotopy category of Zergel bimodules injective. So, so that's a question. And well, this one. So if the Kavanagh homology of a knot is the same as the Kavanagh homology of the unknot, does that mean that the knot K is actually the unknot? So, okay, so what's the status of these questions? Well, the answer to question 1 up is yes. That's, I mean, what I'm blabbing on about, and we'll talk about for most of the rest of this talk. And I gave you I sketched one proof for you at the end of the second lecture. The answer to question 2 up is also yes. In fact, once you know the answer to question 1 up is yes, it follows that the answer to question 2 up is yes. So this categorified Burau representation is a small piece here. So the faithfulness here implies the faithfulness here. Anyway, and I'm not going to explain that in detail, but the answer to this question is yes, and of course, as presumably you all know way better than me, the answer to this third question is yes. This is Kronheimer-Mrowka's theorem. Okay, so what about the original questions, Q1, Q2, Q3? Well, the answer to Q1 is no, except for very small n. So So what's striking here about this picture, I don't want to uncover that yet. So the answer to question 1, no. I mean, so yes when n equals 3, no when n is greater than 4, and open when n equals 4. I have to apologize. I don't know. I meant to look up and completely forgot to look up the attributions for these various facts. So if someone knows, maybe they can shout it out. But. And maybe one other comment is this question, is the Burau representation of the four-strand braid group faithful, has relevance for the question of whether or not the Jones polynomial detects the unknown. Okay. Comments? Questions? So question 1 is no. So question 1 is an example of, so this situation here is a situation I love. That's as someone who kind of works on this kind of mathematics, this is a pretty good situation. So the answer to question 2, well, it's not known. Question 2 is open. It's an open question. Yeah. It's kind of amazing. And since the answer to question 1 is no, that says absolutely nothing about this. In contrast to the blue here, where the question here being yes implied the answer to this question is yes. And of course, as you know, question 3 is open. So unlike Jake, I'm not willing to make bets on any of these things. I have no intuition or knowledge about these sorts of things. But I will root for someone. And as I said, I'm rooting for no for both of these. But I think it would be fabulous if there were some 10 million crossing knot that had trivial Jones polynomial. I think it would really be remarkable. Now, I think what many mathematicians who don't work on categorification would love to see is they would love to see answers to the blue implying something about the white. I too would love to see that. And so I think that's a kind of philosophically general question. I don't think categorification yet has too many applications that way, but it's a subtle question. Okay. So maybe another piece of this which is somewhat similar is you can look in the world of bordered Hagar-Floor homology. There's, as Adam mentioned, the faithful action of the mapping class group of a surface with boundary on a module category for the appropriate algebra. And the decategorified version of that statement is not a faithful action of the mapping class group. It's like the action of the mapping class group on H1 of the surface with boundary or something. It's very, very far from faithful, but it categorifies to something faithful. Okay. I mean, my point of view on this is that currently this is some sort of slight evidence that the braid group is, at least from the point of view of linear algebra, a more natural two-group than it is a group. Okay. Okay, so this question is the one we're going to now talk about a little bit. So let me remind you briefly what the setup is. So we have A is the zigzag algebra. So this algebra, I'm omitting the subscript, so because I think I wasn't even consistent with whether it was n or n plus 1 before. So it's a quotient to the path algebra of a quiver. So we had this oriented double of the type A Dinkin diagram, and we killed some quadratic relations. The relations were all degree 2 in path length. And then we had the indecomposable projective left modules, which I denoted by p lower I for each vertex I. This was, as a vector space, was the span of the paths which ended I. And then we had the homotopy category of complexes of such modules. So the objects here are complexes of A modules. Maybe if we had a grading, so maybe we were looking at graded modules, up to homotopy. And this, this category carries an action of the Braid group. So if the vertices were 1 through n, then this would be the n plus 1 strand Braid group. Okay? And so let me just say, just without going into too much detail about it, the Braid group acts here. So for free, the Braid group acts on the Grothendieck group of this category. So technically, I'm taking the triangulated Grothendieck group. This is a triangulated category. Here I take a vector for each object, a vector for each complex, and I get a relation for each exact triangle. And this representation of the Braid group is the Burau, is the reduced Burau representation. So this guy down here is not a faithful representation of the Braid group, but up here it is. So information about the Braid group is getting lost when you pass from the homotopy category of complexes to the Grothendieck group. So in particular, what that says is that morphism spaces in this category are carrying information about the Braid group that that you don't see, and that's the takeaway from each of these from the proofs I'll describe is they all in some essential way involve morphisms in this category, not just objects. Okay. Okay. So that's the setup. So let me tell you a bit about a couple proofs of this. So the first proof I want to mention today is so only works for the 3-strand Braid group, but it's an absolutely fascinating proof, and it's worth seeing anyway. So when we consider, and again, so that's the 3-strand Braid group. I'm just going to remind you the definition of the zigzag algebra in that case, because this was modulo all length 3 paths. There was a slightly different definition when the small, so this was, maybe I'll call it these are 2. So the 3-strand Braid group acts on the homotopy category of complexes. And theorem, this proof of this theorem is due to Ruquier-Zimmermann. This is so the paper where this appears in print is maybe 2003, but this proof, as I understand it, they knew in 1994 or something like this. So this is an old theorem. The paper is Picard groups of derived module categories. I mean, this paper lives in the world of homological algebra and modular representation theory of finite groups. Has nothing immediately obvious to do with topology. So it's kind of amazing that. So how does this action is faithful, and what's great about this proof is that it uses the relationship between the 3-strand Braid group and the modular group. So that's the idea of the proof. Okay, so remember, so there's an exact sequence of groups. So the Braid group B3 maps to PSL2Z, and the kernel of the action is the center of the Braid group. So the center of the Braid group is isomorphic to the integers. This is the subgroup generated by sigma 1, sigma 2 cubed. That subgroup of the Braid group is central, and you have an exact sequence like this. I still don't want to see that yet. Okay, so here's the. So in particular, to any braid, you can write down a 2x2 matrix, named its image in PSL2Z. Oh, maybe I should define this homomorphism. Get rid of that in the standard generators. So I think this map here takes sigma 1 to 1, 1, 1, 0, and sigma 2 goes to 1, minus 1, 1. So that's the homomorphism. Okay, so so what Ruquier-Zimmermann asks is, so let's say you have let sigma be a braid in B3. So now I can think of sigma as well, abusively denoted the same way, as an endofunctor of this category. So it's an endofunctor from complexes of A modules to complexes of A modules. So in particular, I can look at, so there are two rather basic complexes of A modules, just defining projective A modules themselves, P1 and P2. So P1, which is just a module, goes to some complex, and P2 goes to some complex. And what do these complexes look like? Well, there's some complexes whose terms are a bunch of P1s and P2s, and there are some differentials between them. So Ruquier-Zimmermann ask, what does this complex look like? So in particular, they ask, what are its chain groups? So what are the chain groups of sigma acting on P1 and sigma acting on P2? Now, to reiterate a point that Jake brought up, so here this is a category of complexes up to homotopy. So the question of what are the chain groups is not a priori well defined. It doesn't seem to be well defined. But any complex in this homotopy category has a minimal complex. It's homotopy equivalent to a complex where you've done as much cancellation as possible. And the chain groups of that minimal complex are well defined, up to isomorphism in the category of complexes, forgetting homotopy. So the question of what are the chain groups in the minimal complex, that is a well-defined question. So, so in particular, you can ask, so let's refine this question. In the minimal complex of sigma P1, how many P1s are there? How many P2s are there? Just count them. And here's what Ruquier-Zimmermann proved. Let me call this map pi for a moment. So let pi of sigma be this matrix in PSL2Z. Then the minimal complex of sigma acting on P1 has A P1s and B P2s. Of course, there may be some gradings, there's differentials to make this into a complex. You just forget about that information. You just count the chain groups. See, what's the dimension of the chain complex? This is what it is. So it's captured completely by the first column of the associated matrix in SL2. And for sigma P2, now of course it's so this is an amazing theorem. There are several things which baffle me about it. One, you have absolutely no right to expect such a clean, simple answer for the question of, what is the minimal complex of a braid acting on, I mean, when you take a P1 and you act by a braid, you get some big complex in the homotopy category, so you have to cancel to find the minimal complex. Then you act by another braid, you create a bunch of new stuff, you have to do some more cancellation. So the fact that all of the cancellation you need to do in the homotopy category is controlled by just multiplying the associated 2x2 matrices is completely unexpected. And one way to say how it's unexpected is I have no idea how to generalize this when n is greater than 3. If there's this answer has a, I mean, the input all makes a certain amount of sense. I mean, you have to decide what, you know, what incarnation of the braid group in matrices you want to use, but I don't know. I mean, it's possible that the miracle of this kind of statement is related to the fact that the Burau representation of B3 is faithful, and for higher braid groups it's not. So, so that's almost a proof of faithfulness. Now you just have to reckon with this part of the braid group, but it's easy to check by hand that that the center of B3 acts non-trivially. The center just acts by a homological, the generator of the center acts by a non-trivial homological shift. It just takes a module and shifts it in homology. So I won't even write that down. That's the proof. Okay. Yes?
Is there any, so you could ask, I guess, not only how many copies of P1 and P2 there are, but also like what gradings they land in?
Yeah.
Is there more to this story than measures that?
Let me give you a conjecture. I have thought about that, but I don't think anyone has worked it out. Yeah, I wanted to give that problem to one of my master's students. But, the conjecture is that you just replace this by the 2x2 matrices in the reduced Burau representation. That's got Q's in it now. And then the same theorem holds, and the Q's control the grading. If you ask me what homological degree they're in, that I don't know as a linear algebra question. But as you'll see, in a sense, the answer to your question is something. One way to approach this problem is just to look at the topology of the punctured disk. So we'll give another proof of the faithfulness of this action, the one due to Kovanov-Seidel, and in principle, one could translate the Kovanov-Seidel proof back into the matrices, and that would tell you what the answer is. But yeah, I think if you replace these 2x2 matrices, I mean, if you deform, if you replace these 2x2 matrices with 2x2 matrices in the reduced Burau representation of B3, I wouldn't be surprised if the statement goes through and keeps track of the grading.
Sorry, so
Yeah.
maybe you already said this, but so this tells you how this pi map is defined. I mean, it gives you the A, B, C, and D's. But is there a more invariant way a different way of defining this pi map?
I mean, this is the pi map. This is just
Right. Yeah. So, is there like without using this result?
This has nothing to do. I mean, this is just a fact about the fact that the 3-strand braid group is a central extension of this group. So that's sort of like background information about the group. You don't need anything about this categorical action to be able to define that map.
Okay. Right.
Yeah. I mean, let me make another point here, which about the subtlety of this. This kind of argument does not pass to the Grothendieck group, not in any kind of completely obvious way. It's possible that when you take this complex, whatever it looks like, and you pass to the Grothendieck group, but before it's possible that you could have some further cancellation. Okay. Okay, so now let me tell you the first proof of the faithfulness for all n, which is due to Kovanov-Seidel. For all n. This is the proof of Kovanov-Seidel. And what I want to emphasize in the setup to this is, remember, we're dealing with essentially, I mean, it's a linear action of the braid group. This is an action on a linear category, but it's linear algebra. So what Kovanov-Seidel realized is that this linear algebra at the categorical level is actually capturing some highly nonlinear topology, namely the topology of curves in the punctured disk. So, okay, so let's look here at the punctured disk. So here now, you should be thinking that the braid group, I guess in this picture, would be the n+1 strand braid group. This is a relative mapping class group of this guy. So these are punctures. So we're looking at diffeomorphism from this guy to itself that preserve the boundary pointwise and preserve the interior punctures setwise. So that mapping class group is generated by half-Dane twists around these little curves I'm drawing here, and those guys are the standard generators of the braid group. So is that, anybody want me to say that in more detail? Hopefully that's somewhat familiar. Okay, so in particular, one nonlinear action that one can study of the braid group is the action of the braid group on curves in the punctured disk. You know, you can ask, I can take a curve which starts and ends at some punctures. I can take a mapping class and I can ask where it goes. You know, it's going to go to, you know, who knows what. Who knows? So, so there's an action, an obvious action of the n-strand braid group on curves in the punctured disk. So, so let's say, so the first basic step is a recipe for taking an, I guess, admissible curve in the punctured disk, which starts and ends at punctures, and producing a complex of modules over the zigzag algebra, and producing an object of our category. Okay. And how does that recipe go? Started drawing an example here. So I have these red lines here. So this white line here, so here I have 5 punctures. So this would, so the mapping class group in this case would be B5. And here's a curve. Here's my admissible curve. So I want to take this picture and I'm going to produce a complex of modules of the zigzag algebra. So there's going to be a complex built out of the projective modules P1, P2, P3, and P4. So I'm going to take a bunch of these guys from this curve and produce a complex. Well, I'll do it for this curve in a moment, but first I want to tell you how to do it for some pretty simple curves. So the recipe starts by saying to this curve C1, which is just this little line segment going between the 2 punctures, C1, we go to the complex P1. So just the module itself. And similarly, Ci goes to the module Pi. So the recipe says these simple curves just go to the module. So now if you have something which is not quite so simple, what do we do? Well, the first thing we do is, so step 1 is we're going to orient the curve clockwise. Clockwise around each of the punctures. So let's do that. Oh, actually, well, step 0 is erase the starting and ending segments. So initial and final segments. So that means I'm just going to get rid of this little piece here, this little piece here. Okay, and now with what remains, I'm going to orient it clockwise around the punctures. So note what I get here is not an oriented curve. Each segment is, or each little piece of it is oriented, but the curve itself is not. Okay. So now I'm going to pick this curve up and draw it so that all the arrows are going in the same direction. Okay, and when I mean draw it, I'm going to take all of these intersection points with these vertical red lines, and I'm going to draw the picture. So if I have an intersection point with E1, that's going to be a module P1. So what do I see here? I see a P1. That's going to map in my complex to a P2. That P2 is going to map in my complex to another P2. And that P2 is mapped to by a P2. And that P2 is mapped to by a P3. And that P3 is mapped to by a P4. So all I did here is take the curve out of the plane and just kind of unwind it a little bit so that the arrows are all going in the same direction. And now, well, here's the complex. So I want this to be, so this actually, I mean, as long as these maps are non-zero and none of them are, and this is a minimal complex, this actually, I've defined a unique object in the homotopy category, as it turns out. So what are the possible boundary maps here? Well, something that you may not remember about modules of the zigzag algebra is that there are very few HOMs between these guys. So the space of A module maps from P1 to P2 is one-dimensional. So up to scalar, there's only one non-zero map you could put here. This was paths that end at 1. This was paths that end at 2. There was a unique path in the path algebra from 1 to 2. So composing with that guy is the only thing you can put here. Same thing here. Now from P2 to P2, there were two possible maps. That HOM space was two-dimensional. But one of those two dimensions was given by the identity map. And if you put the identity map here, then you wouldn't be a minimal complex anymore. You'd be able to cancel it in the homotopy category. So there's so if you get rid of this, if you quotient by the span of the identity map, there's only a one-dimensional space of HOMs here. The unique loop at 2. So I'm not even going to bother writing down the differentials because they're determined for you. I also haven't told you which homological degree these guys should sit in, and I haven't put in the grading shifts. That's not interesting and not difficult. So this is a complex. Okay. Now, what kind of curves can you do this for? So I said admissible curves. The only thing you want to be careful about is in your drawing of a curve, you don't want anything like this. If you have anything like this, where there's no punctures inside here, you just replace it by this. Okay?
Sorry, I
Yes.
didn't catch. How do you decide which number, which integers you're taking there?
Oh, you mean which subscripts? I look at so the vertices here are the intersections of my curve with these vertical red lines. And which red line it is tells me which projective module to put down. Okay?
Sorry, before you erase the earlier proof that B3 acts faithfully,
Uh-huh.
maybe a bad question, but maybe you should know this. But so does this argument not work for higher ends because there is no short exact sequence from like B3 to PSL n minus 1 MC? Should I know this?
I don't know how to generalize.
Not B3, but PSL n minus 1.
There are various matrix groups that you could map bigger braid groups to. It is not clear to me how to generalize that proof by using such a thing. So, I mean, in a sense, maybe one way to put it is that, well, okay, I'll say that again after I do this. So, okay, so what have we done? We've done something a little ad hoc. From a curve, we've produced a complex. So there's so we have a bit formally, we have a map from certain curves in D with endpoints on the boundary, etc., to complexes of A modules. And both of these guys have braid group actions on them. Here the braid group is acting as the mapping class group acting on curves in the punctured disk. Here the braid group is acting by tensoring with complexes of bimodules over the zigzag algebra. So Kovanov-Seidel's theorem, I mean, they have several theorems in their paper. This is around 2000. Is that this diagram commutes. So this particular assignment we wrote down intertwines the action of the braid group as a mapping class group on the disk on the one hand and on complexes on the other hand. So in particular, the content of that theorem is that, so let me call this, if this curve was C, then maybe this is R of C. This is what the recipe applies to C. So what the Kovanov-Seidel theorem says is there's two things you could do. You could take your curve C, you could apply a half gain twist, and then you could take the recipe, or you could take the recipe of C, that's some complex, and you could act by the complex of bimodules over the zigzag algebra, and those two complexes of modules are homotopy equivalent. Okay? So in some ways, this is somewhat analogous to some of the things that Liam was saying about curves in the torus. I mean, to some curve in the torus, you have an object in a DG module category. It's maybe somewhat similar. Okay. Corollary is that the corollary gives the action of the braid group over there is faithful. So why? So corollary. Bn acts faithfully on the homotopy category of complexes of A modules. So this is so the proof I'm about to give is not the proof that's in Kovanov-Seidel's paper, though I mean it's using one of the things they prove in their paper. Their argument for the faithfulness of this used a relationship between bigraded intersection numbers of curves in the disk and HOMs between the complexes in the category. So there are lots of ways to take what they did and produce proofs of faithfulness. But so by the recipe, if you have a braid which is not 1, it suffices to show that sigma of one of these basic curves Ci is not isotopic to Ci in the punctured disk. So you start with one of these little curves. If you act by a braid and you get a curve that's not isotopic to it, then this recipe will take the complex Pi to a different complex with more terms in it. So, okay, so it suffices to think about braid sigma such that sigma of Ci is isotopic to Ci for all I. So this is now no longer a question which has anything to do with linear algebra. This is just a question about the mapping class group action on curves in the disk. We're asking which braids, thought of as mapping classes, would take this curve to itself, etc. For all of those. So what curves do that? So now here's an exercise. So So again, we're letting CI be this curve in the punctured disk. Show that beta, well, sigma of CI is isotopic to CI for all I, then sigma is a power of the full twist. I mean, it's a central element in the Braid group. So, which is, just copy the integers. Okay, so armed with this exercise, the recipe tells us that the kernel of this action has to be contained in the center of the Braid group. And now it's easy to see that the center of the Braid group acts non-trivially. The center acts by a non-trivial shift. Take a central element, and you act on a PI, it takes it to, if it's a non-zero central element, it takes it to a non-zero homological shift of PI. That's a computation that one carries out here to check, to finish the proof. Okay? Okay. So that is, that's Kovanov-Seidel's proof. There is there's a ton of magic in here. I mean, I think a kind of fun game is to take things about the Braid group that you can understand via curve diagrams and translate them. So one exercise I did that I was going to include in the lectures, but didn't, but it's worth pointing out, is the Denois left invariant order on the Braid group has a nice interpretation in terms of curve diagrams on the disk. So you can translate that via the Kovanov-Seidel theorem and give a purely homological algebra formulation of the Denois order in terms of the representation theory of the zigzag algebra. So things like that you can discover very nice statements by just chasing through this recipe. Yeah, so maybe let me, before, there's one more proof I want to give you, but just a couple comments about maybe things that might be interesting to do for someone who wants to think about these sorts of things. So, did I write any of this down? Well, okay. I mean, okay, so what are some, a couple questions that this suggests looking at that I don't think anyone has thought about? These are rather vague questions, but still I think there's maybe something there to think about. So, now these are maybe related things, but one is so how is the dynamics of a braid thought of as a mapping class group reflected in the homological algebra and the action of the braid on the module category of the zigzag algebra? So for example, if you give me a pseudo-Anosov braid, how can you tell whether the braid is pseudo-Anosov just by looking at by the complex of bimodules, or by acting on a module, look at the complex of modules. So how is this dynamics reflected in the action of sigma on this category? This is maybe not such an unreasonable thing to think about because, well, one of the ways that one might try to understand the dynamics of a mapping class group element would be to take a curve, to hit it with the braid, and to study how the curve becomes complicated by looking at intersections with lines like this and seeing how the number of intersections grows. That's exactly what we do in this recipe. And that recipe tells us how the complex grows in terms of how big the chain groups get, how many modules are in the chain group. So maybe let's just put as a second thing, what can you say? What can one say about the growth of the complexes beta acting on a pi, yes, beta to the k acting on a pi as k gets large. I think this is potentially an interesting question. In particular, people who study things like infinite full twists in the Braid group and Kovanov-Rosansky homology and things like that, the homological algebra that's required to think about this kind of question is probably the same as the kinds of things you do when you study the infinite full twist and Jones-Wenzel projectors and things. And then maybe another slightly even vaguer question that I'm also interested in is maybe related is well, if you like things like laminations and train tracks and those kind of objects, whatever they are, can this Kovanov-Seidel recipe be extended in some meaningful way to points at infinity in the space of curves on the disk? You have a curve on the disk, maybe you act by higher and higher powers of the braid. That curve goes to something, some point at infinity in some appropriate moduli space. So can one extend the Kovanov-Seidel recipe to something involving infinite complexes? Infinite but stabilizing. Well, just say infinite complexes. I promise, and I don't think this is a particularly difficult thing to believe, that the homotopy category of unbounded complexes of modules over the zigzag algebra is also controlling some interesting topology. Okay. So any questions about this this proof and things? Yes?
So you mentioned that this faithfulness, this proof faithfulness essentially incorporates some analysis of morphisms.
Uh-huh.
Is it, can you see that?
Yeah, I mean, it's completely hidden in the differentials in this complex. It's completely hidden in the statement of in the proof of the main statement, which is that you can take a curve and produce a complex, and then act by the Braid group action on that complex. I mean, understanding that, the Braid group action on the complex, understanding that is all about morphisms. That's where the morphisms are. Or you can act by the curve and then do the recipe. So the fact that those are those two complexes are homotopy equivalent to each other, that's a statement which requires knowing something about the differentials. Yeah. And I mean, again, keep in mind that there'd be no hope of doing something like that at the level of the Grothendieck group. Well, I mean, not in a way that would tell you the action on the Grothendieck group is faithful, because it's not. Okay. Right, and just to recall, so maybe as the last thing, just from a slightly different point of view, I want to rephrase a bit of the proof I told you last time. So another kind of proof. Well, actually, this one I'll pose as a question because it's not really worked out. So for those who know what these things mean, show directly that that a connected component of the moduli space of Bridgeland stability conditions on this triangulated category is contractible. So here, the point is that this is, again, and I say this just to bring up another sense in which there's interesting topology hidden in these linear 2 representations. So the Braid group action acts linearly on this triangulated category. And what you produce from that is an action of the Braid group on this this stability moduli space, which is a complex manifold. Whatever the definition is of it, it's a complex manifold. And this space, what is this space? It's some covering space of of a hyperplane complement whose fundamental group is the Braid group. So the appearance of the Braid group as a fundamental group here is important when you're studying stability conditions. So the faithfulness of this action here is equivalent to the statement that this space up here is the universal cover of this hyperplane complement. So in fact, it's not just the universal cover, in fact, it's contractible. So that's an even stronger, so somehow I bring this up because this is an even stronger statement than the faithfulness. It's known, but I think the existing proofs use the faithfulness as one of the ingredients. So it would be nice to have a direct proof of this. Okay. And then finally, a kind of last and this I won't give too many details on. So final kind of proof. So this is what O.L. Queffelec and I did, and one of so we gave a couple proofs of the faithfulness of the action, and one of them used very heavily earlier ideas of Prof. Thomas, is that one can use the action of the Braid group on this homotopy category to define metrics on the group. So in the metrics we define here, we then subsequently prove can be identified with some word length metrics, like the word length in the generator of positive permutation braids, or word length in generators of atoms for the dual Garside, the Berman-Collie Garside structure. So, so these metrics are related to various positive monoids, positive, strongly quasi-positive. These monoids can be detected in here, and you can use similar things to actually define metrics on the group. So there's some geometric group theory, which is also hidden here. Okay. So maybe that's what I wanted to say about a few of the different faithfulness proofs. So just one final remark to try to connect this zigzag algebra stuff to Kovanov homology. So connections between the Braid group action on this category and Kovanov homology. There are two. There are two connections, I mean, at least two connections, but there are two rather independent connections. The first, so suppose you have a Braid group action, and you want to produce a link, you want to try to produce a knot or link invariant from it. So then you want to do something which is, you could interpret as maybe being related to the closure of the braid. So if we were dealing with the Braid group action on the homotopy category of Zergel bimodules, then Jake told us what to do to get triply graded link homology, namely take Hochschild homology. So anytime you have a categorical Braid group like this, you can always take Hochschild homology, and you can see what you get, and see what it's an invariant of. It'll be an invariant of Braid conjugacy classes. Whether it's an invariant of anything else, well, maybe it is, maybe it isn't. So here, if you take Hochschild homology, you do not get Kovanov homology. You do not get an invariant of links in S3. What you get, so the Hochschild homology of the complex of bimodules you get here, of the zigzag action, is a piece, and piece I mean a particular k-graded component, so of what's called sutradanular Kovanov homology, which Ellie alluded to and didn't say too much about, but this is a particular invariant of links in the parameterized solid torus. It had a bunch of gradings on it, one of which was this K grading coming from the SL2 action. And one of those K-graded pieces is what you'll get if you take Hochschild homology of this. Okay. And the second is you can soup up this action to give a construction of Kavanagh homology. So if you replace this algebra A by something a little bit more complicated, by the smash product or wreath product of the symmetric group with A, so that's like you take n tensor copies of A, and the symmetric group acts by permuting them. This is like a semi-direct product. Then the Braid group action on the category of modules here induces a Braid group action on the category of modules here. I mean, here this should be SM. This has nothing to do with the... and you can try to use that Braid group action to define a knot invariant, and it won't quite work. But what's kind of miraculous is that this slightly larger algebra actually has a lot of Braid group actions on it. It's got like a toroidal Braid group's worth of actions on it instead of just ordinary Braid group. And inside the toroidal Braid group, there's a lot of copies of the finite Braid group. And if you choose one very carefully, then you can use that Braid group action to give a construction of Kavanagh homology. So this is sort of unpublished work of mine with Coutus. So construction of Kavanagh homology, essentially using this zigzag algebra. So those are the two connections to Kavanagh homology I know of. I think philosophically what you should keep in mind is in this sort of world of Braid group actions and knot invariants, this is the simplest one. Whether or not you think it's simple depends on your case, but this is the simplest one, and there's probably still some other things to explore about it. Okay, I'll stop there.
Can you say in terms of curves what's happening when you pass through these more complicated modules?
It's effectively like taking a symmetric product for the curve. More precisely, well, maybe I can tell you more precisely. I mean, it's better to say it's related. So this original A appears in algebraic geometry in the algebraic and symplectic geometry of the resolution of the type A simple singularity. So this is a complex surface whose derived category has a Braid group action on it. That's very much like the zigzag algebra is an endomorphism algebra there. And passing from there to there is like going from this to the Hilbert scheme of m points on the space. So Hilbert scheme is kind of a souped up version of symmetric product. It's like it's a good version of symmetric product of a four manifold.
So, I mean, are you essentially recreating Seidel-Smith?
No, I don't think so.
No. Looks very similar.
Yeah, I mean, somehow they're I think that this could be wrong, but so the Braid group action here induces a Braid group action here. That Braid group action does not give you a link invariant. But Seidel-Smith worked on something which is like a deformation of this. So one way instead of deforming this, something else you can do is you can define a completely different Braid group action on it, which is a bit hidden. That's what we do. I mean, there's more symmetry here than the symmetry here, and you exploit that. I don't completely understand it.
So the hyperplane arrangements, that's I think that's the classifying space for your Braid group. And so that the stabilizing manifold is sort of the universal cover, the EDG. And so I'm wondering if there's a classifying category. There's a category that's sort of the classifying category of VM, so that the homotopy category of modules over that A is sort of its universal Does this make, okay, I'm just
I
trying
mean,
to
I think,
lift it.
no, I think the point is that
Okay.
this universal cover already appeared as the Bridgeland moduli space here.
Okay.
There's lots of categorical break group actions which are going to probably have the same subsume moduli.
Right. But is there a notion of classifying categories? Like category
Yeah, I mean, if you think, I think if you think about
associated to the
groups,
braid
two
group?
groups, higher groups, etc.
Okay. All right. Okay.
I don't know what the
Okay.
precise
Sorry.
statement
Okay. I'm
is.
just
It's
trying to
and that's a
I guess
reasonable.
I'm just trying to lift